We've shown in graphs 10.6 and 10.7 how it is that price-distorting taxes give rise to inefficiencies as a result of substitution effects. We will now illustrate how we can show the same thing, the inefficiency of price-distorting taxes, on graphs with marginal willingness to pay curves. In the top panels of our graphs, we'll again have the consumer diagram, and we'll go through the sequence that we went through in graphs 10.6 and 10.7 to illustrate the difference between lump sum taxes and distortionary tax payments. We begin again with the blue before tax budget constraint. The imposition of the housing tax then causes a steepening of the budget constraint as the price for housing increases from P to P plus T. To find the actual tax payment that's made under this tax, we have to know where the consumer optimizes after the tax is imposed. This gives us the optimal bundle A with consumption level CA and housing consumption HA. Had the consumer consumed the same level of housing prior to the imposition of the tax, she would have consumed bundle alpha, giving her a consumption level of other goods equal to C alpha. The difference between C alpha and CA is then once again the tax payment that is made by the consumer under the distortionary housing tax. The highest possible lump sum tax that we could have extracted from this consumer without making her any worse off than she is under the housing tax would involve shifting the blue budget constraint inward in a parallel way until it is tangent to the after-tax indifference curve at bundle B. And the vertical difference between the blue and the green budget lines represents the lump sum tax payment that would be made under such a lump sum tax. That difference can be measured below point alpha to give us the distance L, which is larger than T because of the presence of the substitution effect from A to B. The size of the inefficiency is the difference between L and T, which is labeled here as DWL, which stands for deadweight loss. We can now transfer some of the relevant information from the top graph to a lower graph where we again measure square feet of housing on the horizontal, but this time we measure price of housing on the vertical axis. Bundle A, for instance, drops down to point A at the height of the price P plus T, in other words the after-tax price at which A was in fact the optimal bundle in the top graph. Bundle B, on the other hand, happens under the lump sum tax where the price of housing wasn't changed. So as bundle B drops down to point B, it settles at the before tax price P. Connecting A and B in the lower graph, we then get the marginal willingness to pay curve that corresponds to the indifference level that contains bundle A. Now let's focus on this lower graph. The difference between the higher and the lower price is just the tax rate T that was incorporated into the increased price for housing. Note that this little t is different from the capital T in the upper graph. The capital T in the upper graph is the total tax payment that is made under the housing tax. The little t, that's the difference between the before and after tax price, is just the tax payment that's made for each square foot of housing. Now we know that this consumer consumes at point A if the housing tax is imposed. Thus we know the consumer consumes HA square feet of housing under the housing tax, and little t is just the tax payment the consumer makes for each of the square feet of housing that she consumes. Thus, little t times HA is equal to the total tax payment that she makes. Little t times HA is equal to the rectangle B. Thus, capital T, the tax payment that is made under the housing tax, is equal to the area B in our lower graph. Under the housing tax, when the consumer pays P plus T and settles at point A, we know that the consumer surplus is the area above that price below the marginal willingness to pay curve. In other words, the little area A. When the consumer pays a lump sum tax instead and ends up at point B in our lower graph, she pays the lower price P instead of the price P plus T. Thus her consumer surplus under the lump sum tax is area A plus B plus C. Now notice what we've concluded. At point A, under the housing tax, the consumer surplus is area A. At point B, under the lump sum tax, the consumer surplus is area A plus B plus C. Thus the consumer surplus under the lump sum tax is B plus C higher than it is under the distortionary housing tax. But if we look at the top graph, we know that A and B happen on the same indifference curve. Thus the consumer is equally happy at bundles A and B in the top graph, and must therefore be equally happy at points A and B on the marginal willingness to pay curve. That seems initially puzzling, because if the consumer is equally happy at points A and B on the marginal willingness to pay curve, how can it be that her consumer surplus is larger by the area B plus C at point B than it is at point A? The answer is actually pretty straightforward. How did we get this consumer to consume at bundle B in the first place? We didn't change the price. Instead, we took cash from the consumer in a lump sum way, and the amount of cash that we took away from her must be exactly offsetting the increase in consumer surpluses she gets by not having had the price changed to P plus T. Thus, we can conclude that the lump sum tax payment that we've taken from this consumer to make her equally happy between the lump sum tax and the distortionary tax must be equal to the area B plus C, the area of additional consumer surplus she gets from not having had the price increase from a distortionary tax. Thus, L, the lump sum tax payment, is equal to area B plus C. Since the deadweight loss is equal to the difference between L and capital T, we can then conclude that the deadweight loss is equal to the area C in our graph. We've said repeatedly now that the inefficiency or the deadweight loss of a tax arises from a substitution effect that in turn emerges from the price distortion that's caused by the tax. We can then once again illustrate how the removal of the substitution effect removes the inefficiency of the tax and thus the deadweight loss. We begin in panel B again with the before tax budget constraint. The increase in the tax on housing is again assumed to distort the price by raising it from P to P plus T. To remove the substitution effect, we now again assume that the indifference curve is one that treats square feet of housing and dollars of other goods as perfect complements. The optimal bundle A again has consumption level CA and square feet of housing HA. Using the bundle alpha on the before tax budget constraint, we can then again illustrate the tax payment T that is made by this consumer as the difference between C alpha and CA. The most that we can take away from this consumer in a lump sum fashion is the amount that shifts the original blue budget inward to a point of tangency or quasi-tangency with the after-tax indifference curve UA. Because of the perfect complementarity between housing and other goods, the point we called B in panel A now falls right on top of point A. Thus, the substitution effect that caused the deadweight loss in panel A is now no longer present. As a result, the highest lump sum tax payment L that we can raise from this consumer without making her any worse off is exactly equal to the actual tax payment T that she makes under the housing tax. Since there's no difference between L and T, there's no deadweight loss. We can then again translate the information from the upper graph to a lower graph with square feet of housing on the horizontal and the price of housing on the vertical. Bundle A happens on the magenta budget constraint in the upper graph, in other words, the budget constraint with the after-tax price P plus T. Thus, as it drops to the lower graph, it settles at the high price P plus T. Even though bundle B and bundle A happen to be the same point in the top graph, bundle B emerges from the lump sum tax budget constraint, in other words, the green budget constraint, with the lower price. Thus, as bundle B drops down to the lower graph, it settles at the lower before tax price. Connecting points A and B in the lower panel then once again gives us the marginal willingness to pay curve for this consumer, given that she's at utility level UA. Since marginal willingness to pay or compensated demand curves only incorporate substitution effects, the elimination of the substitution effect through the assumption of perfect complementarity results in a perfectly vertical marginal willingness to pay curve. The difference between the higher price P plus T and the lower price P is then once again little t, which is the per square foot tax that's incorporated into the price of housing. Multiplying this little t per square foot tax times the total square feet consumed, HA, then again gives us the total tax payment T, which is equal to the rectangle B. The consumer surplus at point A, at the higher price P plus T, is again equal to the area little a. The consumer surplus at point B, at the lower price P, is equal to the area A plus B. But the consumer is indifferent between being at point A and point B. Thus, the increase in consumer surplus from being at point B must be exactly offset by the cash that we took in a lump sum tax in order to get the consumer to point B. Thus, the lump sum tax payment that we were able to extract from this consumer must be equal to area B. In other words, capital L is equal to B. And since the deadweight loss is equal to the difference between capital L and capital T, there is no deadweight loss in this case. By looking across the lower graphs of panels A and B, you can see how the deadweight loss triangle from the tax disappears as the substitution effect shrinks down to zero. The substitution effect is what causes point B to not lie right underneath point A. As that substitution effect gets larger, it moves point B further to the right and further away from point A, and this in turn causes the triangle C, the deadweight loss triangle, to increase in size. But as point B moves to the left and eventually underneath point A, that deadweight loss triangle gets smaller and smaller until it disappears. In other words, it is the substitution effect that's responsible for the deadweight loss triangle that emerges under the distortionary tax. And as the substitution effect disappears, so does the deadweight loss triangle.